Good morning, my name is Mihalic and I'm going to present you the project Sonification of light spectra. Started in last September as a collaboration between the Musinfo and PIM laboratory at Aix-Marseille University. I represent the association Musinfo and I will be alone today, because my colleague Alexander Escarguer from PIM laboratory is currently at the Conférence in Sweden. Very fun. The purpose of association Musinfo is research on computer music, and PIM laboratory makes research on the plasma. The purpose of our collaboration is to find auditory solutions to the data obtained in the laboratory. Okay, regarding the contents of the presentation, I will first shortly present our project. Then I will explain what the plasma is and show you the instrument which the plasma is produced. This is the part of the conference of Alexander Escarguer. Thereafter, I will shortly explain what the sonification is. And I will show you two projects close to our current work. Then I will show the results of the first two steps of our project. And finally, I make some conclusions. The project is divided into 4 steps. The first one is the creation of a software for the sonification of light spectra and establishment of database for making comparison between timbre from the spectra of various light sources. Then, this testing of the software with the spectra from plasma. And following the results from steps 1 and 2 will make changes and improvements in the software in order to obtain real-time sonification and to compare the relevance of the auditory results with the visual results. And the last, we will use the results in an art project. We have now realized that the first step of the project, and we are currently in the second one. The third and fourth steps will be realized next year. Okay, so what is plasma? The plasma is one of the 4 states of matter, together with solid, liquid, and gaseous. Plasma is composed of the charged particle. It is not found on Earth, as it attains temperatures well above the average temperatures on the planet for the plasma to exist. However, the plasma represents 99% of the state of matter in the universe. And we can find it in the stars, in Earth's ionosphere, and in interstellar environments. The plasma is ionized gas. It's a mixture of positively and negatively charged particles. This mixture is not stable, so if we do not maintain a plasma, it disappears and becomes simple gas. On the right side of this photo, you can see here, you can see what the plasma created in tokamak looks like. I will tell you after a little bit more. Only the edge of the plasma and its visible light. The center of the plasma, which is extremely hot, emits ultraviolet or X-ray, to which our eyes are not sensitive. And why we create plasma is to create energy. The fusion energy is one possible way to create energy. This energy source needs to create plasma with a temperature as high as inside the heart of the sun. This technology is not yet mastered and is sterilized. If we succeed in this task, it will have several advantages over fission technology. I remember fission technology is technology used in Chernobyl or Fukushima, for example. It's why we tried another source of energy. One possible way to succeed in fusion technology is magnetic confinement with the tokamak configuration. It's like this. The first one was made by Russians in 1968. It's a very old technology. Nowadays, ITER It's an international tokamak supported by China, European Union, India, Japan, South Korea, and Russia. It is under construction in Cadarache, near Marseille. It will complete it in 2018. It is supposed to prove that magnetic fusion energy is profitable technology. More energy is created than that is injected in. Now, to support major projects as is ITER, many research laboratories in the world work to conduct projects of fundamental plasma physics. The Mistral machine here in the PIM laboratory in France is an example of this. PIIM stands for Physics of Ionic and Molecular Interactions. The laboratory is part of French National Center for Scientific Research. Mistral is an experimental device that produces a plasma column plunged in a magnetic field. This plasma column is in white in photo here, and here's the plasma here. Researchers are studying how the plasma behaves in this magnetic field, essentially by optical diagnostic. In particular, we study the plasma by analyzing the light it emits. The plasma light is dispersed just like sunlight is dispersed by a prism. The dispersed light is the spectrum. This diagnostic, called spectroscopy, allows us to obtain a lot of information on the plasma state without disturbing it. The information about temperature, density, composition, and so on. The two photographs you can see show the two plasma spectra of visible light, corresponding to two different states of the plasma. One is hotter than the other, and the light emitted by the plasma is also very different. Thus, looking at the spectrum of the plasma, we obtain the signature of the state. And here you see the corresponding spectra for the two plasma on the former slide. And now, what is sonification? Through sonification, we are able to perceive the spectral data through our hearing. A commonly accepted definition of sonification is that it is the use of non-speech audio signals to convey information or make data perceptible. This procedure allows the observer of an event to perceive the changes of values audibly rather than visually. One of the first instruments, and certainly you know it, of sonification is the Geiger counter, invented in 1980. Since then we can find many applications of sonification, such as the sonification of solar winds, the sonification of data from space shuttles, or sonification of data from Etna volcano. And here is the first of two projects that preceded the sonification of plasma spectra. But it's close to the current project now, and is working with Spectra 2. That's why I presented it a little bit. It is software that we created at the University Institute of Technology in Bourges, and it used for sonification of diffractometer data. We will not go into technical data, but we will just listen to the results of two measurements. We can hear that one of the main features of the sound resulting from sonification are the beats, periodic changes of intensity of sound like a slight tremolo. Sound was presented to scientists. These beats were the first thing they perceived, because it's very nice. We soon realized this beat is due to an inherent defect of the diffractometer itself. And the second example is sonification of celestial objects. Here the temperature of the star is deduced from its spectrum, and the star is ranged into a stellar classification. The sonification is done using subtractive synthesis, where the sound source is white noise. Each celestial object is represented by one filter. The stellar classification is transformed into a filter frequency, and the magnitude of this object is transformed into filter amplitude. The position of the sound in space depends on the position of the star itself. In this way, we can perceive the auditory characteristics of the constellations. The sonification allows us to perceive the differences between the constellations through the sound timbres. Each constellation has its own characteristic sound. Here are some examples. Astrological sign can contact me afterwards. Okay? Finally, here is an example of all constellations composing the zodiac to hear all constellations and to hear the changes in real time. Let's go speak about the project. Now I'll speak about the first step of the project. The project consists in the creation of a software for the sonification of spectra and the establishment of a database. For acquiring the spectra, we used the spectrometer OVO. You can see the photo here. This is a portable device, a bit like this. I'm sorry I have it with me because it's used in Marseille now. And this device can be plugged into the USB port on the computer. Using the spectrometer, we created a database of spectra from various sources, and then we sonified these spectra. The goal is to perform auditory comparison of different light sources. Here are the data after the acquisition. The spectrometer records into a file the data of light intensity for different frequencies. The result is of this is curve, okay, and sequence of values. And the values are read by the sonification software, which then transforms them into sound using the sound synthesis. This process is currently not in real time. Therefore, we have first files recorded on the hard disk. The files contain the results of measurements made by the spectrometer. After that, the sonification software reads these files and produces the corresponding sounds. Here are some examples of data from database. You can see only the sources. And here is the program called Patch for the sonification of spectrometer data. This program is created with Max MSP software. The program recreates the files with data of intensities from the spectrometer. and converts them into sound by using the additive synthesis of 128 oscillators. To create the sound synthesis, we must first determine the range of audible frequencies. The software proposed the possibility to automatically create a range of values between minimum and maximum frequency. The curve of each spectrum then determines the individual amplitudes of each oscillator. This curve can be changed in order to remove or add frequencies whose amplitude does not exceed a certain limit. We'll see it a bit more after. The software reads the files recorded by spectrometer directly from the hard disk. These files are circuited in menu. And for more clarity, we have selected some files with images of the light sources in order to compare them visually and orally. Okay, here are the sources of white light. We have 4 sources. The first range, you can see sun and candle and light. And here are the sources of the blue, yellow, red, and green light. And to compare now these same colors with the comparison to other sources, same colors but other sources. The first and second. Blue, yellow, red, green. Okay. And finally, here's a comparison of the white light sources, the last range, with the source of a low energy light bulb at the last here. We can hear a clear distinction between the first 3 sound chambers and the last one, although the light we see is white each time. Okay, the light is the same, it's white, right? Okay, we see light, but the sound is completely different. Here's again the comparison of the same source during changes in amplitude in order to eliminate or add frequencies with low amplitude to change the sound per se. Something like cleaning the sound only to hear perception. Okay, and now I will talk about the second step of the project currently in process. The second step of the project is the sonification of the spectra produced in the Mistral machine in laboratory of PIM. Unlike in the previous step, here we examine the evolution in time of typical spectrum of helium plasma. The spectrum changes over time according to the experimental conditions, the changes in temperature or in density of plasma. These changes are followed by an evolution in time of the amplitudes of the peaks. When the conditions of the plasma vary, the intensities vary as well. The data structure is no longer the same as it was for the static data measured during the first step of the project. As we can see from the picture, we get a succession of peaks changing over time. We can see the values in columns here. The graphical presentation of data here. And the evolution of the spectrum over time here. and we are at the evolution with sound. The software is another version of the one used for sonification of diffractometer data. It is still using the additive synthesis to produce the sound, but this time with 9 oscillators whose values or amplitude change together with the spectrum of plasma. To sonify data, the software generates an interpolation between the values of input and output for the amplitudes of the oscillators. This interpolation may be linear or non-linear. The configuration parameters are in the central space of the software here. By changing these parameters, we modify the audio results to make them more significant or for auditory perception. In this way, we obtain a sound whose amplitude changes over time. Here's an example of the sonification of the spectrum of helium plasma. The sound synchronized with the movie. And here's the second example. Here we change the frequency interpolation, and the result is frequency shifting on sounds. Okay, to conclude our presentation, we can say that sonification can give us valuable information about the plasma state. As we have seen, the results of the first step of our project are clearly perceptible. Now we will create a new software to manage data in real-time acquisition. And the second step of the project, which is in progress, is already very encouraging. In the end, the sonification will be used as another solution for data presentation of plasma spectra in a PIM laboratory. However, the sonification can also be used for purely artistic purpose as a source of inspiration. In fact, a future step will be the creation of an audio installation and a musical composition based on the scientific data from our research project. Thank you for your attention.
Yes, excellent for this presentation. I think we have just time for one or two questions. Yes.
You said that the real-time sonification of the plasma spectrum uses 9 oscillators.
Yeah.
And are these oscillators spread on the whole spectrum, or do you search for the peaks in the spectrum?
And now we look only for the peaks.
For the peaks,
yes. Okay. You know, it's one of the possibility. Now we study because the first one is why I show you the spectra of stars oscillation. It's another solution for sonification. We are trying now how we can hear what is really significant to hearing. Yes, we start with filtering or with additive synthesis, or we can make another solution. But this is the first solution, and for the first solution we like to make something very simple, and to have the hearing really
look for the peaks and
for the peaks. Yes, it's why we are. Use the software for diffractometer data, because it's additive synthesis with 20 peaks to make it additive synthesis, and it's the same like for spectra from plasma. I received the files with data and with 9 peaks, like I showed you, and after I put it in the software, we have here. Yeah.
So why did you move from subtractive synthesis to additive synthesis?
that's a practical composition or an aesthetic one?
It's, the first filtering, it was aesthetical, because it was started to make a composition. Okay? But we take it from musical and from that from stars. And it's only aesthetical to have, you know, it's noise like data coming from outside, and after filtering only the 1 point is something aesthetical, and after it was more nicely than once since after, of course, we made the additive synthesis to have really exactly sound.
One more question. So that means if you try to get a more artistic approach to this data, it would be more the data itself you would use, and to rebuild the synthesis, because now it seems that the synthesis was completely more pure, and just to bring up the characteristics of the data to help the scientists to work with it as another space of perception. So this would be a process you would rebuild to get a more artistic approach.
Yes, the sonification is it will be something like to make a material from musical composition. So it's something like all touches of the piano, and after you choose some touch for composition, something like this. You have material, and after you choose artistical approach. Okay, but it is not the same approach for scientific, but the start is the same. Thank you.
One more question. Thank you for the presentation. Yes, for the last percent of this session, I would like to introduce to you Ms. Mihalic.